Hi, everybody. Let's start with this microphone, and somebody might just pop in and help me fix the other microphone. So welcome to the final week. Now you have me. You all know me from the messages and other things. I'm Yoni, just a schedule. So we're here, obviously. So we've got roughly 2 hours and 50 minutes of machine learning, right? This is not going to transform us into machine learning professionals. But it actually might, within these 3 hours and the project, you might actually just have enough to be employable as a starting position in machine learning, assuming that you do other things, right? There's no promises here, but it's sort of infinitely more than nothing. So you have project 3 obviously out. It's been only edited today. So or published today. So what was out there up until today was a draft, or well, it was what we had last year. But you can go and look at project 3, and later on, by the end of today or tomorrow, let's see how time works. We'll spend some time on project 3 as well. The practical is also useful for project 3. Any questions before we get going? No, everybody's happy and ready to go. All right. So a taste of machine learning. So, okay, so let's pause for a sec. Hey, how you doing? Yeah, it might be me. I just, this one doesn't work. It's not you. All right, so actually, I'll just continue. Yeah, so machine learning is probably almost as old as the digital computer. So it started in the 50s together with the advent of computers. But it's simply that in the past maybe 60 or 70 years, most programming has been done. It was procedural, was algorithmic, like you've seen with sorting, like you've seen with the simulation, modeling, numerics. It's mostly been kind of very well-defined algorithms. Whereas when you get to something that is a machine learning computer algorithm, these are soft algorithms. The computer kind of sees what we do and mimics it. That's kind of the idea. I must say that up until about 20 years ago, it was more of not such a mainstream. It was more of a hobby thing. And in the early 2000s, you started seeing machine learners. Well, what I want to say, it wasn't kind of everywhere. Now it has exploded. So about 20 years ago, you started seeing machine learners looking at ads, kind of web pages based on your history, what ads to show you. I remember thinking for myself at the time, as a young researcher, this is not exciting. I mean, why spend all this effort just to kind of just to have pop-ups for people of this is what we're going to show them. But since then, of course, we use machine learning daily in apps in very natural ways, auto completion of text and other things. Let me just show you one demonstration. I don't need to demonstrate it too much, but just in case you don't know this tool or tools of this sort. So say you have some picture of something mathematical. Let's go for this one, for example. So this tool, for example, which I kind of like, even though it's not free, but I just use it a bit, so I get the free tier. It's called MathPix. Does anybody know it? Super useful when you're doing presentations, lectures, and more. Only now I have the typical problem with Zoom, so hold on a sec. Just put this down, so the Zoom pen will disappear. It's a bit hard with Zoom, so one second. I'm just gonna, what I'm doing is I'm clicking on something that's like a, I want to wait for this top pane to disappear. Not do it with well, basically, maybe if I could. All right, so with Zoom, I cannot do it with share screen because Zoom is blocking my kind of icon for clicking this thing. But basically, by highlighting this thing, for example, what MathPix image, which is pixelated image, and it can be also on a on a text document that's scanned from the 50s. MaxFix will give me the LaTeX code. Just very useful. I mean, if you're making presentations and or whatever, and cool things from documents where you just have thanks so much. Where you have yes, but you don't have the you don't have the the actual LaTeX source. This thing does wonders. Yeah.
But it's machine learning differentiated itself from just pattern recognition and it's like it's fairly formulaic in the sense of symbol.
Right. So within this world, there are about several competing terms. You've got deep learning, machine learning, artificial intelligence, pattern recognition, data science, data mining, statistics, and in general computer science. So right, all these things kind of intersect. Some people would go and give you very precise definitions, what machine learning is, what pattern recognition is. Machine learning is a form of pattern recognition, but the techniques have also moved on into, thanks a lot, into pattern creation and, data creation, augmented video, etc., control decisions. So when you think of pattern recognition, just going to change this a bit. So when you think of pattern recognition, you're just looking at something, want to understand the pattern. Whereas when sometimes you actually want to control things or you want to generate things. So yeah, but these are all competing terms. And indeed, machine learning had this, you could call this small subset at the time that was called deep learning. Way from the 50s, 1958, Rosenblatt had something called a perceptron. But what happened about 10 years ago at around 2012, but building up to it, obviously things happened before in research, is that deep learning just flew. And now deep learning is just killing it in many ways. It's a machine learning method of choice when you have ample homogeneous data. Not always, there are other methods as well. So at UQ, we have a STAT 3007, a deep learning course, created and taught by Nan Ye. There's STAT 3006. That's a statistical learning course. That's much more of a mathematical course looking at properties of learning. So the statisticians around the year 2000 were a bit offended. They were, all these computer scientists are coming and they're calling themselves machine learners, but actually using stats. So then this movement came of calling things statistical learning. Okay, that's kind of the statistician view. But at the end of the day, these are very similar concepts, sometimes with different paradigms, but they mix together. And, that's you'll find stuff like this in STAT 3006, but also a lot of theoretical stuff. And then you've got STAT 4401. That's kind of an advanced statistics course. And sometimes it has more of a machine learning flavor. Sometimes it has more of a statistical flavor. So there's kind of a spectrum between the two. And when you speak about AI in general, there's not really a definition. I mean, when you speak to people like, I don't know, university vice chancellors or all kinds of administrators like that, then, for them, AI is just a thing you put on things because they're smart dashboards. But really AI in the past decade has been kind of deep learning. That's maybe a thing. And of course, I should mention this course, Comp 4702, the most associated academic with this, or I think the creator, etc., is Marcus Gallagher. So this is kind of a proper machine learning course for computer science, that's focused on machine learning. Okay, so that's kind of this world in a nutshell. And there are multiple terms. So we're not going to do kind of a full machine learning course in these 3 hours, but rather you guys already know how to code. In various forms, and now you'll see this style of coding. Okay, but it's really, our course is code centric. So you're actually implementing something and understanding something. So there are a lot of aspects of machine learning theory and practice that we'll kind of not touch, obviously, in this very brief unit. 2 terms to know: supervised learning and unsupervised learning. I always found these terms kind of difficult. What's the story? But basically, supervised learning is maybe what you are doing now. You're being told something, you see examples, you kind of know what's right, what's wrong, even though we didn't give you solutions to big homework, right? But this is supervised learning. Unsupervised learning is a toddler or a baby not being told what's happening, but still moving around the world and exploring. That's kind of the things. Okay. Now, if we go a bit more concretely, machine learning almost always has to do with data that comes from the real world. Sometimes this real world may be a mathematical model that's actually creating a pseudo real world, but often maybe the real world can be what's it called, that
Some of you might have played this with the bricks. Minecraft, that one, right? So maybe the real world is that kind of real world. You can do machine learning on Minecraft, but it's some sort of something that through this kind of dashed line generates this data. So when we look at this data, well, you could just think of it. You just spent last week speaking with Andy on data frames, right? So you can think of it as like a very big data frame in a sense, where the rows, if you'd like, are observations and the columns are variables. And in machine learning, we call the variables features. So if we have an image, we'll look to that image data. Each pixel is a feature. Or if we have an RGB image, each pixel has 3 features, the R, the G, and the B. Okay, so many features. So often you have many features, and you have many variables, many observations. So many variables / features, many columns and many rows, many observations, many samples, many data points. And the general assumption of machine learning, kind of in the base assumption is, that the process is homogeneous. Now, of course, when you're actually working in practice as a machine learning engineer, the process is rarely homogeneous. You have to worry for, you're learning what spam mail is based on one language. It's not going to be spam mail in a different language, et cetera. Or there are even trends over time, et cetera. But in general, when you have these X's, which are the features here, and you have this much thinner column Y, that Y is called the label. That's the variable we're trying to predict, okay? That's the label. So the features and the label, okay? This setting is generally called supervised learning because we're seeing for every sample here, for every row X, we're seeing what is a Y, okay? We're seeing the label, okay? We're seeing images of digits, and we're saying that's digit 7, etc., or for each image. And what we do in machine learning, there are basically two main activities. So one activity, like has happened here with this, this demo that I tried to show you and didn't work, with this MathPix thing, right? The model is already trained. They did this offline. They ran on probably JSTOR documents on thousands and thousands of documents, and they had LaTeX source. And they also put some human-made rules, but it was quite automatic, I'm sure. I don't know what they did in practice, but it must be a machine learning-based algorithm of sorts. And then they're supplying a model. So the model, then what you do in the model is you get one example, this X tilde, this one row, this one example, and you give one prediction, right? I gave an equation, a picture of an equation, and as a prediction, I actually got the LaTeX source for the equation, right? Now, the training process happens here, okay? And this is more the lengthier process. So this is a process that the machine learning engineer does, and that is use a learning algorithm to create the model. And these things are sometimes mixed. So sometimes models continue to be adapted as things work, okay? So that's supervised learning. Unsupervised learning, you don't have Ys, okay? A baby learns about the world. Well, they're very supervised, but they're not supervised in their learning, right? The baby learns things in the world. They're not told this is a dog, this is a cat. They just learn to associate after a while the difference between a dog and a cat. Okay, so unsupervised learning has all kinds of different activities. Here are 2 illustrations. So one, for example, that's very common is clustering. So I've done before some consulting project for a company that had customer data, okay, just a lot of customers. So each row was a customer, and they wanted segmentation of the clustering of the customers to different clusters. That's often a bit arbitrary, but if each cluster, it's like a permutation of the data, such we have cluster 1, cluster 2, up to some specified cluster K. Okay, so that's often useful because we know, oh, these are of this type, that of a different type, et cetera, right? I mean, that's, for example, what biologists have done to, all of the animals in the world, right? They've clustered them into different groups, right? I mean, of course, through not such a simple clustering algorithm, but that's what's been done. Sometimes clustering can live in a model, and that could also interact with the real world. A different form of supervised learning is data reduction. So data reduction, which you can think of just as compression, but it's not necessarily compression for the purpose of sending a signal from one point to another. I mean, that's what's happening with everybody at home or being recorded, et cetera. I'm speaking and stuff's being compressed, but it's being decompressed kind of perfectly. This is more compression from a statistical perspective to really get the essence of what is there. So if you had, for example, 10,000 features, you might end up with only 100 or only 50. Okay, so you get kind of low dimensional data. So we'll see quick examples of that. So that's kind of unsupervised learning. Our focus is going to be on supervised learning. okay, in the project and the rest of today, etc. But just so you know, so supervised learning, when people kind of speak about, oh, you're doing some pattern matching, as we said, some machine learning, okay, that's supervised learning. Learn the pattern Y based on features X. Okay, so let's actually get to some business. Now, in the world of machine learning, you have example data sets. Okay. And you also have data sets that are proprietary, owned by a company, owned by researchers, or that people create. But typically without real world data sets like this, and we're speaking now about supervised learning, that have X and Ys, you can't do much. No data, no machine learning. By the way, you can do some stats without data almost, right? You can do Bayesian stats and a bit of modeling, et cetera, and maybe just put a few data points, some sufficient statistics and stuff like that, but that's not machine learning. Machine learning needs data. Actually, a lot of the job of the machine learner, you would have heard this from Andy also about the data wrangling, and you would have heard this from the Perspective seminar speakers, is dealing with the data. Okay. I've done consulting this year. I was on long service leave during the first half. I did consulting for a very exciting kind of fire emergency company. And a lot of the work was actually annotating data sets. Annotating means you actually put labels on the data set saying, what is this and what is that and what is this and what is that. So that's annotation is a huge industry of itself. But in the world of machine learning, you also have open data sets that are used both for practice, what we're going to do here. But interestingly, they're not only used for practice, they're also used for application and research. So what do I mean? So we're going to look at some very basic data set that's called MNIST. MNIST is some, I don't know what, we need to click and see what it is exactly. I forgot the acronym, but it's, I don't know, National Standard TTTTTT. And people created 60,000 pictures of images, of digits. They look like this, 28 by 28 pixels, monochrome, okay? So each pixel is maybe a number between 0 and 255, or maybe it's a float 64. I think it's a former, okay? But that doesn't really matter, that quantization, okay? I think there are 255 values, but I'm not sure, okay? And X, this 5 here, that 28 by 28, which is 784 features, 784 pixels, that would be one X, that would be one row, that would be one data point. And the associated label is this integer 5. And for this 0, the associated label is this integer 0, etc. So that's what the labeled data looks like. So MNIST is probably not what is used by pattern recognition systems that you have when you exit the shopping center mall and the barricade sees your license plate automatically, right? Or Queensland police sees that you're driving too fast and, you know, does all this in a streamlined process. Nobody even needs to look at it and you get the fine, right? So MNIST is not the data that's used for that. It's really used for practice. However, there are other data sets that are used both for practice and are openly available. So the most famous, I don't have an example here, but just need to say it for a second, is ImageNet. So ImageNet has about 1.5 million colored labeled images. It's both used for courses, for if you do a deep learning course at UQ, you'd probably deal with ImageNet, etc. But it's also used in practice to train models and then retrain them for something else. Okay, so what I'm saying is this kind of world of machine learning data sets is a big world. And and the data sets are both openly available and used both for practice and in practice, for studying and in practice. So let's look at this ML data set. So we have a package in Julia, it's called ML data sets. And in this way, this looks rather Python-y with these dots, but these are modules. The ML dataset module has an MNIST module inside it, and inside it has the train data function. And the train data function, you tell it, well, do I want the data as float 64s or float 32s or float 16s, etc. There's been actually a trend in the machine learning world to reduce from float 64s to float 16, all the way down to float 16s for high performance on GPUs. Still haven't said GPUs, but deep learning has become a huge thing 10 years ago. Due to the video game revolution that happened about 20 or 30 years ago, right? So video games pushed the GPU market, graphical processor unit market, right? And then all these GPUs became available and it became easier, sort of easier. It's still very hard to deal, not very hard, but it's troublesome to deal with GPU drivers, right? So the GPUs have kind of made deep learning possible. I digressed all because of a float 64, but let's get back to this. So we've got trained data here. Okay, so trained data in this case, and let's actually look at it. So I actually put this in a Jupyter notebook. So if I run this, so trained data has, well, it looks very big, right? But what you see is it's a combination, it's both a tuple and has arrays. If I look at the length of trained data, it has two things. The first element is going to be the features, and we call this the images in this case. And the second element is going to be the labels. So if I put, you see, I've put trained data as images, and if I look at train images now, so that's the first element of trained data, it is a tensor in this case. It doesn't have to be represented as a tensor, but it's a tensor. It's a 28 by 28 by 60,000 tensor. Okay. So how many images do we have? It's no calculation needed. Is it 28 or is it 28 times 28 or is it 60,000? 60,000, right? So what they've done is they've kind of put the first dimension of the tensor is like the vertical coordinate, second dimension of the horizontal coordinate, or maybe it's the opposite, and then 60,000. Sometimes other machine learning packages won't give you things as a tensor. They might return things as like an array of arrays, okay, etc. But this is actually, most of the chances are, by the way, if you're going to do machine learning out in industry, it will not be in Julia. But this course is not here to teach you Julia, it's to teach you about computing, right? You might use Julia very well. So, I mean, we think it's great. That's why we're using it. But the machine learning world is using Python. And there's much more Python support for machine learning than Julia at the moment. That might change. Julia is a bit specialized in special machine learning, something called scientific machine learning, which is kind of for much smaller models that involve more modeling. Okay, so in Python, for example, this is how you'll get that. The main packages in Python, scikit-learn, PyTorch, TensorFlow, you might have heard these phrases before, etc. Okay, so that's what the images are. And if we look at the labels, we got 60,000 labels, and they're just integers. It tells us what, that's that column of Y, right? So by this, what we've seen is we've seen here the data like this. We've seen the, you know, each row is a 28 by 28 image, okay, schematically, and each column is just an integer Y, is a label. Okay, so great, and we see this. Now, we'll speak about this a bit more later, but the paradigm, the basic paradigm in machine learning is to take the data you have and split it. If you don't think any further, then you'll split it into something called a training set and a testing set. Okay, there's further splitting. You might split the training set into also something called a validation set. We'll speak about this just a bit later. But in general, this is a training set and testing set. And the idea is very simple. It's not complicated like the statisticians do with small data, because data is very costly for statisticians, right? I mean, there's kind of, 500, 600 observations, 700 observations, then you need models and p-values and things like that. With machine learning, you train on the training set, and then you see how it works on the testing set. Some caveats there. If you continue to work on the training set and then test so much on the testing set is, and you go back and train, that's called overtraining. The testing set is no longer a testing set. You've cheated. So for example, MNIST has 10,000 observations in the testing set, and that's kind of a bit, perhaps a common split, right? Like 1 in 7 for testing and 60,000 observations in the training set. But that testing set has been used by tens of thousands of machine learning papers, because almost any machine learning paper in the past 20 years does some benchmarking on MNIST research papers. I mean, there have been a lot of advances, a lot of research papers. Okay, so we see the size of the training set and the testing set. And here we can plot. So here are the digits from the training set, and here are the associated labels. Okay. Okay. Okay, we've got data. So now let's see if we can do something with it. So first of all, images are kind of hard to work with. So instead of thinking of images, let's apply the vec function. If you don't know the vec function, then, well, now you know the vec function. In Julia, the vec function simply takes a matrix and vectorizes it into a vector. I think it does it column-wise, but frankly, it doesn't really matter because as long as we're consistent, you know, we can do column-wise vectorization or row-wise vectorization with an image. That's what vec does. And if we do this, VCAT is going to be applied to this comprehension of vectors, which we took here and we did the transpose of each vector. So to actually treat it in this case as a row, and we're using the ellipsis, the splat operator. So VCAT is going to do vertical concatenation of this. And in this case, what we've done is we're putting all this in one big data chunk. So this is in a sense a reshaping. You could have done this in different ways. And a lot of what you do when you handle these kind of data sets is first is this type of reshaping. So you need to kind of experiment and see you're doing the right thing. So what we're doing is we've just put it in one big matrix that has 60,000 observations and 784. What would you call these? What are some names? 784, 28 by 28, 28 times 28. Some words we use, this is the language of it. You can say multiple answers. Yeah. Factors. Okay, factors not so common. Factors, but you know, first of all, you just say pixels. Second, say features, variables, columns. Right? That's what there are. Right? Okay. So again, we're just to put you in the mindset. We've now put this 60,784. Okay. All right. So that's what we did with this big X. And this X, it's big, but you know, on today's laptops, it's not so big. Let's just plot it. Let's do a heat map of this X. Okay. So here you have 60,000 images. Each row is an image. Why are these vertical black lines here? And why are there no stuff here, no stuff here? So we're each one we've vectorized an image. We move this way. So to the left of the image and to the right of the image, there's not too much, and above and below, there's not too much, and then that's this pattern. Okay. All right. It's sometimes good to look at the data. You can't do this with a massive data set. I mean, this is not a massive data set for a laptop anymore. This is running on my laptop, right? But this is a whole data set, 60,000 by 784. Here, what we're doing is we're taking just the same thing, but we're just doing a sort perm. Sort perm, of course, is just going to sort the data set according to the labels. Okay, so it will return a permutation. I won't say the permutation because there are many, many permutations because the labels are not unique. There are only 10 labels, but this is a permutation of the labels. So basically now it put about 6,000 of the first rows are for the digit 0. And about 6,000 for the second row are for the digit 1, up to the 10th kind of chunk here, right? There's 6,000, so this is a digit 9. Right? This still doesn't mean much, but we already see when you look at this image, you could see, oh, well, I might be able to kind of find differences between, you know, zeros and ones and twos, right? It's kind of just a bit of a different view. Okay, it doesn't hurt to do. By the way, when you do handle data and you do training and testing and you pull out a validation set and do all the things, you don't want the data sorted. You actually want it shuffled. Okay, you want randomization. I mean, randomization is a concept both for statistics and machine learning is a good thing because, well, we're removing any potential biases that we had. Okay, so good. So we see now the data. So with this data, soon below we'll go and we'll do some classification on this data. But now let's still take just a bit of a digression and be on unsupervised learning. Okay, just so you have about 10 minutes of kind of a taste of unsupervised learning, and you'll see this elsewhere in your career probably. Haven't looked at the chat to see if there are any questions at home or any comments. Just go ahead. All right. So there's simply two demonstrations here. This first one, and this is, we're not going to go in depth into this. Paul Bellett also spoke about PCA, and he also showed you singular value decomposition, principal component analysis. So the basic, who's used PCA here before, by the way, or at home? Anybody on YouTube watching later has used PCA? We don't know. You're not watching. Okay, so, well, you're not here now. All right, so PCA, principal component analysis. The general idea is to take these we have 784 columns here. Okay, this is a very, look, there's only zero, like 1 to 760,000 observations, right? 784 columns. So what we can do is find linear combinations of these columns, okay, into a different space, where that space ideally won't have 784 columns. Maybe it'll have 2 columns, 3 columns, 5 columns, etc. And we want to do these linear combinations in the right way. Practically, what the computer is doing when it's running PCA, it's simply solving an eigenvalue problem, and it's ordering things according to the magnitude of the eigenvalues, and the kind of the eigenvector associated with the first eigenvalue tells us what is the most meaningful direction. That is sort of what's happening. Okay, or you can look at it as diagonalization of the covariance matrix. But from a user perspective, and many scientists use PCA without thinking about eigenvalues, or PCA can be framed within singular value decomposition or things like that. From a user perspective, what PCA does is it lets us take a digit image, which is 784 dimensional, can't visualize that, and put it, for example, as you see here, just look at this one. So this is just comparing the digits 0 and the digit 1, but for a second, ignore the color, ignore the blue and ignore the red. Each point here is a digit. The actual, so let's take this specific point. Let's zoom on this point here. So the actual fact that the first principal component for this point is like just over 5, and the second principal component is somewhere between -5 and -2.5, doesn't matter. But it allows us to look at that point next to other points. Okay, so this is a form of data reduction. We say, well, what we see actually here, and if we now for a second momentarily return the labels, and this is just points that were digit 1, they're about 6,000 points here, and points that were digit 0, they're about 6,000 points here. We already see something interesting. We see that by projecting from 784 dimensions onto 2 dimensions, we can already find quite a nice separation between digit 0 and digit 1. Okay, so many people have done this, and then, for example, one machine learning algorithm would do the following, would pass some line here. So here's now with this an algorithm, a machine learning algorithm, to just separate zeros and ones, okay? So ignore the other digits. Assume our data just had zeros and ones, right? Assume we're just looking at handwritten digits in the binary world, zeros or ones, okay? So do project onto the 2 principal components. So then each digit can live like here. I'll put like a digit, you know, 1 digit might be here. Okay, or this is just their digit, a single digit. Let's say a digit fell here. And then we see where it is relative to this separating hyperplane. Okay, there's a whole branch of machine learning, a whole bunch of algorithms called support vector machines. They were very popular and they're mathematically beautiful up to the rebirth of neural networks in about 2012. Okay, support vector machines do this. They find these separating hyperplanes. Okay, so what you see is principal component analysis can help with that, but it also helps with other things. It's kind of often an aid for other types of analysis. This data reductions is in general a good thing. But again, there's no physical meaning to PC1 and PC2. And PC1 is a linear combination of all 784 pixels, and so is PC2. So with this demo, what we're doing is we're just showing not all digit pairs, but just showing some digit pairs. And you see that some are separated by 2 principal components and some are not. Okay. All right, so that's one form of unsupervised learning. And a different form is clustering. I've spoken about this before, like above. And that's also extreme. This is very useful. Has anybody used clustering here in one way or another? No, or at home? Oh, it's not hard to use. I mean, here is, look, actually, we're using a package in Julia called clustering, and we're using the k-means function. And k-means doesn't like to have X, it prefers X transpose because that's the interface. So it prefers to have the columns be the observations and the rows be the variables. And in this case, we're telling, hey, k-means, please give me a clustering result which assumes 10 clusters. Okay, and what it's just getting the data of the images, and it's going to get 10 clusters. And it's basically a mapping saying, hey, this image and this image, they're together in the same cluster. This image and this image, they're not the same cluster, etc. Just imagine, does anybody here know how to read Arabic letters? Numbers. I don't know, but Arabs invented the decimal system, I believe, but now they actually use numbers that are, the characters are different. But as a human, all you need to do is you need to look at, the 10 Arab digits, 0 to 9, right, for about 5 minutes, and you'll know these are the same digits, these are different. Okay, so that's what the algorithm is doing for us. It's kind of stupid to do this for the digits here, but still what's interesting is that in a cluster, in this k-means clustering algorithm, k-means is a name, that's the most kind of simple clustering algorithm. Okay, you also get a center of a cluster. So these are the 10 centers of clusters. Now, these digits don't really exist. They're averages in 784-dimensional Euclidean space. Like this one is an average of some number of digits that were said to be similar to each other, right? And we see that sometimes we got things that are very clear, but sometimes, like 4, 7, and 9 probably mixed up, etc. So if we had just a bit more time, we'd explain how this k-means works. It's actually a very simple algorithm. It's a heuristic. The clustering doing optimal clustering under some optimality condition is like an NP-complete problem. It's intractable, but this is a heuristic that's so powerful and used a lot. But let's not dwell on k-means, only if we have more time at the end of tomorrow, like how the algorithm works. But it's quite simple. It basically just iterates between finding a center and seeing who's near the center, and then refinding a center and seeing who's near the center, etc., etc. Am I going too fast? Okay, I haven't seen students' faces this year. Are you students? No. Okay, good. No. End of semesters. No, and you're the ones that have come to class. Okay, thanks for coming. All right. Supervised learning. So we're done with this little excursion of unsupervised learning. So with supervised learning, you can break the problems into, if you want to do some further dichotomy, let's just do this, sorry. So, sorry. You can break the problems into something called regression problems. And that's obviously a very highly used word, like linear regression, right? Linear regression is actually a regression problem, but regression in the machine learning world means that that the label you're predicting is a continuous variable, okay? So that's a regression problem. So for example, looking at a person's face and knowing their blood pressure, right? The blood pressure you can treat as a continuous variable, that's a regression problem. Or, as we'll focus more in this short unit, on classification problems. Classification is, you're saying it's from a finite set. It's a digit 1, it's a digit 2, it's a digit 3, it's a digit 4. Classification can be binary. It's either 0 or 1, or it's either a dog or a cat. Okay, or classification could be multi-class classification. Your project actually deals with some subtle issues. So the second part of the project, the first part deals with a Melbourne housing data set, but the second part deals with subtle issues of taking binary classifiers and fusing them together to create a multi-class classifier. Okay, so we'll now let's see how to create a classifier that looks at a digit. Okay. Going to look at one of these guys and tells us which label it is, 0 to 9. It's actually surprisingly easy to get 86% accuracy. It's pretty good. So it's kind of like simply with least squares, with linear regression. It's not industrial strength. Okay. It's not industrial strength. So state of the art on MNIST would get about 98 point something accuracy. Okay. So that's kind of getting close to, what you'd expect from say a system that, that does identification when you exit the shopping center mall and it reads your license plate. There, it's not just digits, it's also letters, right? But this is pretty good. Okay, just we'll get 86% accuracy. Now, in a full machine learning course, one will spend quite a lot of time speaking about performance measures. I mean, what do I mean by accuracy? I tell you 86% accuracy, and you understand, oh, by 86% accuracy, what he or I mean is, 86 out of 100 digits are classified correctly. For MNIST, it's fine to use accuracy because the data is balanced. It's roughly balanced. There are about the same number of zeros as ones, as twos, and threes, up to nines. In other cases, getting 86% accuracy is horrible. For example, if you look at biomedical stuff and you look at me and say, okay, do I have cancer? And you tell me 99% I don't have cancer because it's just not so prevalent, luckily, okay, and et cetera, and this age, et cetera, blah, 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 blah. So, you know, that accuracy, 99% accuracy of not having cancer is not the right thing because the proportion of people that have at a given time, given the, you know, the testing is low, right? But let's not deal with that, but just keep that in mind. You know, if you go and you work later, unbalanced data sets are a whole other issue. Okay, these data sets we're working with now are balanced. Okay, so what are we going to do? So we already saw how we created this data matrix here. Okay, this is kind of our data matrix. And this is going to be the strategy. The strategy is simply that we'll treat each row here. I'll purposely put like a square over a row. I have no idea what happened here now. Air conditioner, let it be. Oh, rain? Something. All right, we continue. So say that I obviously highlighted more than one row, but assume that this is only one row. Okay, so assume that these are 784 pixels in there. So let's just do a linear combination of each of these pixels, okay, to get a value. Okay, so an inner product of some weights with each of these pixels. And let's also put what we call a bias term or an intercept term. Bias is one of the most highly overused words in machine learning. So some people speak about ethical machine learning, ethical AI, where data sets have bias for one gender or one race. That's like one thing. That's one form of bias. Sometimes there's bias when you do estimation and you're kind of off, systematically off. That's a different type of bias. Our use of the word bias here is just a y-intercept. Like when you do simple linear regression, the y-intercept, okay, in this case. So what we're going to do is we're going to do this linear combination. However, what we're going to also do is we're going to just speak about linear classifiers, sorry, binary classifiers beyond this linear combination. So we're going to do like an observation, a prediction is going to be beta 0, that's the bias term, plus 784 features, just like multiple linear regression if you've done a bit of stats or something like that. But the other thing we're going to do is as data, let's only learn for a single digit if something is a digit 3 for a single digit type, if something is a 3 or not a 3. Is it a 4 or not a 4? Is it a 5 or not a 5? So we'll do 10 different models like this. And then we'll fuse these models together. So we'll do 10 different binary classifiers. So we're going to transform the data. We're going to take, like, I'll go back to the data a second. So let's take the labels. So this is the labels of the data, right? So if, for example, you look at this and all we wanted to know if something is a 1 or not a 1, then we'll put on this 5 a -1. This 0 is a -1. This 4 is a -1. And this 1 is a +1, like positive sample, negative samples. -1, -1, +1, -1, +1, -1, -1, -1, etc. So we should have about 54,000 -1s and about 6,000 +1s. Okay, I mean, we could have done not -1, +1. We could have done 0 and 1, but that's just kind of easy. All right, and what we're going to do is we will. So we treat, it's just like doing now least squares, where this here, what you have is a sum of squares. This might look a bit nasty, but basically this beta vector is a 785 dimensional vector. And we will multiply it, we'll do an inner product. This is an inner product with the 784 observations and that 1 for a bias. So the first element of beta is this beta 0. And we'll subtract from that what we expect to have, a +1 or a -1. Okay, so this is what's called our loss function. Now, I didn't say the word loss function yet today, but most of machine learning, and certainly all of deep learning, not all of machine learning, but most, is loss-based. What does that mean? We actually pose the problem of learning as an optimization problem. We engineer a loss function that's useful for our purpose, and we minimize that loss. Okay? That's kind of the name of the game. So learning is in a sense optimization. Okay, and a lot of kind of the techniques have to do with what kind of loss function to choose. For linear models, a squared loss is natural. You've had this also in Unit 3, etc., because then the theory of least squares works well and many other things work well. So now some of these mathematical details have already appeared a bit in Unit 3. I think I have Unit 3 open here. So here around Unit 3, let's see, when you had, is it Unit 3 or Unit 2? Yeah, Unit 3, sorry, I'm just in the wrong place. So that was with Paul Bellet. I don't know how we got up there. There we go. So there were also, these types of things were also in Unit 3, and that was solving least squares problems, which is minimization of the sum of squares. Statisticians call this linear regression. The statistical linear regression model has more. It also has assumptions on the noise and stuff like that. But that is in terms of optimization, what we're doing. So mathematically, what we can do is we can actually have this matrix, which is going to be like the data matrix. Okay, the superscript is the observation, n running from 1 to 60,000, and the subscript being the feature. So we've got P is 784 in this case, and we have this other column of ones. Okay, so this is how we create this matrix. We're just concatenating a ones matrix, 60,000 ones, with the data vector that we had before. And this is a loss function seen a bit more nicely. This is the L2 norm squared. Okay, so you can treat it as as this vector. That's a vector inner product with this vector. All right, and with a bit of kind of calculus, a bit of multivariable calculus, what you can do is you can actually take the gradient of this thing. So this is a function from 785, from R785 to 1. A loss function is always scalar valued. You're minimizing some loss, okay? And you're living in 785 dimensions, okay? Because in this case, we have 785 features. Well, we have 784 feature plus what we call the constant feature, right? So in these models, the number of parameters that we're going to optimize or learn is equal to the number of features. In other models, for example, in deep learning models that we're not going to get to, so they have many layers. Well, they're kind of more, this is a deep learning model, but it's a very degenerate deep learning model. So there you sometimes have many more parameters than features. Okay, so there's kind of all these things that live around. And if you would take, you can represent the gradient of this thing. So that's the derivative of this loss with respect to each of the 785 coordinates. And it has this very neat matrix expression. Often in more general machine learning, deep learning, we don't have this beautiful luxury where we have an explicit expression for the gradient. Okay, so, but you've already heard a bit from Paul Bellet a long while ago. There's this thing called automatic differentiation, and you also did numerical differentiation techniques, right? So you can compute the gradient that way. Automatic differentiation, much more common than numerical differentiation this way. Now, in this case, and you would have seen this in some of the courses, maybe even in Math 2001, I'm not sure, right? So then you can equate this to 0, but there's different ways to get to this. You can also get to it through projection or different arguments. And this is what's called the normal equations. Okay. Now, if A transpose A is non-singular, so A transpose A is a Gram matrix, going to be a square matrix. Okay, it's a 785 by 785 matrix. If it's non-singular, which will happen if and only if this, you need a bit of linear algebra for this, but that's a side comment. If the columns of A are linearly independent, okay, so if A is full rank, then you can actually, multiply by the inverse of this, and you got this thing that's called A dagger. Now, actually, if you were to do this if you were going to try this for MNIST, for that big matrix, which we've shown you, the columns are not linearly independent. Just look at the data and tell me, why are the columns not linearly independent? Why the column? I mean, the A matrix is this plus one other column of ones. Why are they not linearly independent? I mean, you got a lot of dark space, a lot of zeros, right? So you actually, cannot use this type of formula. And when you use kind of statistical packages, actually like GLM and also in the R language and others, when you're doing least squares, it actually does this. Well, it doesn't compute the inverse. Often when you solve linear equations, you don't compute the inverse and multiply by the inverse. You use kind of state-of-the-art linear equation methods. But bottom line is this thing is going to be singular, but nevertheless, this matrix A dagger, which is called the Moore-Penrose pseudo-inverse, still exists. And I think Paul Bellet also showed you this briefly, and you can just get it using the P-inv of A. Okay, so the nice thing about P-inv of A, you apply it to the labels and you get the parameters. I mean, this is like super cool, super simple. Most machine learning is not like this, but with linear models, it's like this. So here we're not doing any iterative procedure. There is an iterative procedure for computing the A dagger. This P-inv did a whole lot, but we're not doing anything iterative in the sense of kind of running in a loop, as you'll soon see. Okay, and the size of the pseudo-inverse, it's going to get, it's a matrix that converts 60,000 labels of +1 and -1, and gives you 785 dimensions. It gives you this beta. Okay, so let's see in just 3 lines of code how this is done. So Julia, and we'll take a break just after this. So Julia's deep learning package is called Flux. The analogy in the world of Python is, and other languages as well, but really Python is TensorFlow, PyTorch. Keras is a wrapper for TensorFlow. There's also FastAI. Here, Jeremy Howard is at UQ. You might have heard of Jeremy Howard. He created FastAI, and he's now an adjunct at UQ. FastAI uses PyTorch under the hood. There's a whole bunch of frameworks. Julia has a Flux framework. We're not actually going to use a whole lot from Flux here, except for this one very little function, one-hot-batch. And what one-hot-batch does is it converts a label 7 into a, for example, 7 into a vector that has 0, 0, 0, 0, 0, 0, 1 at the 7th position, 0, 0, 0, 0. That's called one-hot encoding in the world of machine learning. Okay, so that's in a sense just a technicality. So what we're doing here is we're taking the labels and converting it into kind of vectors that are either zeros or ones. That's a bit of a technicality. And this one-line function here, and this one just takes an x and either, if it's positive, it gives it +1, otherwise it gives it -1. Okay. So what we're doing here is we're creating the Y data. And here, after we've computed the pseudo-inverse once, we just need to compute the pseudo-inverse once. This gives us an array of the betas. So we didn't do here one problem. We did 10 problems in parallel. We learned if a digit is 0 or not 0. We learned if a digit is 1 or not 1. We learned if a digit is 2 or not 2, up to digit 9 or not 9. So with these betas, almost done with this example, and then we'll take a break. Here's how we can create a classifier. So what's a classifier going to get? It's going to get a square image. A square image, we are here agreeing that it's a 28 by 28 image. Okay. So what is it going to do? It's going to do exactly this. It's going to put the image like this here as a vector and add to it a 1. Okay, so let's see that. So here is the vector of the image, and here is 1. So this is now a 785 dimensional vector. And then it's going to multiply it, do an inner product that dash times, it's going to do an inner product with each of the 10 vector of learned parameters. We have 7,850 learned parameters. It's going to do that with each of them. Okay. And for each one, it will see what is kind of the highest score. So +1 means it's like, it very much thinks it's like a 7, you know, if it's positive, it very much thinks it's that digit. It thinks it's a 3, it thinks it's a 5, it thinks it's a 9, etc. And it's just going to use the built-in Julia function argmax to see what it is. What is it most likely? So this is called one versus rest, or one versus all. So you're actually using 10 binary classifiers. And that's actually the essence. This is part of your solution to one of the things for the project with one versus rest, one versus all. So you have 10 classifiers, and in each classifier, you're seeing which is most likely. This last subtraction of -1 is simply because in Julia indexing is from 1 to 10, but we want digits from 0 to 9. Okay, with Python or with zero-based indexing, things would have been a bit nicer. So now let's apply this linear classify on each of the test images. Okay, so this, right? So we're taking, remember test images was a tensor. So we're ignoring the first two coordinates, or we're taking all of them, the colon, the 28 by 28. So what I've highlighted now is like one image. Okay, what linear classify is going to do is going to return something between an integer between 0 and 9 inclusive. And then let's check the accuracy. So ignore the confusion matrix for just a second. Just look at this line. Oh no, we do need the confusion matrix. Okay, so the confusion matrix is the rows here are what the actual digit was. The actual digit was 0. The actual digit was 1. The actual digit was 2. The actual digit was 9. And the columns are what was our prediction. Okay, so we're creating here with this double comprehension, the confusion matrix. Do we like a lot of numbers on the diagonal or not? The confusion we like, right? So numbers on diagonal mean we weren't confused. So what was kind of where did we see a lot of confusion or some confusion? This one, 80. So 80 is 0, 1, 2, 3, 4. So what does this 80 mean? A lot of 4s were thought to be 9s, right? A lot of 4s were thought to be 9s, okay? So this is kind of a post-analysis tool. And this is running on the test set, on images that we didn't look at. And the accuracy, one way to look at the accuracy is the diagonal of the confusion matrix, that dividing by the num test, which is 10,000. There are 10,000 numbers here. Of course, there are tools to actually plot the confusion matrix and stuff like that, right? But we're just showing it. And the accuracy was 86%. So that's it. That's actually not so hard to do machine learning. I mean, it might seem like a lot of details, but these details are with the same level of complexity as you have when you're just learning about least squares, and you've used least squares for many other things. So here we're just using least squares. Whoop, we're getting an 86% accurate classifier. The computational engine, which was hidden under the hood here, was the pseudo-inverse. The pseudo-inverse actually solved, in a sense, the least squares optimization problem. By having the pseudo-inverse, that's what we get. It's important that I also show you, go back to unit 3 and then really take the break. Why is this not? Oops, sorry, pressing the wrong thing. Do this. So in unit 3, there was this bit of code where, we used you might want to just look at this bit of code in unit 3 that simply solved the least squares problem on like 5 data points. It's something very small, but it doesn't matter. Here we solved it on a lot of data points. Okay. And there were a lot of different examples on how to solve the least squares problem. So this was one of them with the pseudo-inverse. That's what we use now. A different example, a different method was a gradient descent method. What we're going to get to after the break is this type of approach, which doesn't use like here's a system of equations, let's solve the system of equations, and it'll do something iterative under the hood with the state-of-the-art kind of linear algebra packages, but rather do this iterative optimization that goes all the time in the direction of the gradient until it settles down. So that's what we'll look at after the break. But you already saw this very briefly in unit 3, so just wanted to highlight that. Any questions before the break? No? All righty, so let's meet in, it's 6, oh, time flies when you speak. Okay, so let's meet at 6:07. We'll continue then. I'm going to be brave enough and pause the recording. Let's see.
So, Julie is actually a fancy for like semicolon is not registered as the normal semicolon. So, three question marks. And the three question mark looks exactly like a semicolon, and most fonts are indistinguishable. Often used to play jokes, because I appreciate the semicolon, but the line says it doesn't the semicolon kind of jokes. For a lot of things like Julius, you know the micro sign is the same as me. People say, oh, they're different Unicode things, but we're going to treat them as the same code point. It doesn't do it with the Greek question mark. So if we put it in the okay, no, it's just that.
What's micro?
Yeah, so if you go like so Unicode has two different code points, the micro symbol and the Greek letter mu.
Yeah.
So if you write the
Julia.
you wouldn't do it like but like if you're copying a first thing text, that might be a really common occurrence, or if you're copying a variable name, you're not going to get the same, which is one of the main using emojis and variable code that we want to quickly identify which is which. And hence why I think it's good we need that they don't also have to create a question mark as a semicolon.
What's a great question mark? What does it look like?
Exactly like a semicolon.
Oh, really? And used in Greece today or oh, back in the days?
Yeah. No, but great question mark looks like it's so like to get the Unicode character.
Oh, I didn't know. Okay, really? And it's not a semicolon,
No,
right?
and like
Oh.
Julia is pretty good for a lot of things.
Oh, but does this not appear as a very big thing in Julia? Have you tried it?
So like if you copy this. In comparison.
Get my glasses.
So if we use emojis as variable names, will we get marked down?
No.
Zoom in. Which one's the Greek?
Oh, I
question mark?
cannot see. No.
Which one's the
yeah, yeah.
semicolon?
Oh, interesting.
You want-
But you know, Thomas used to have different fonts on his Julia, so that you can actually do that. I don't know how.
Well, like a lot of symbols it does really well. So like micro and mu, which
Yeah.
are the same Unicode, different code points. Mu. See?
What's different? What's micro? I know mu. I don't know micro.
It's the because Unicode isn't it looks exactly the same, but Unicode, even though they have different
And this sets up now mu. Okay.
values.
Oh, they actually treat them. They've done some merging table.
Yeah,
I
just
see.
it's a merging table,
Right.
but
Not
some
for that.
characters are not.
You know, open the first issue in of yours. I assume the first in the Julia language. They like these things. So yeah, go ahead and use emojis.
I just thought it was a bit of a weird thing to this out, but no, feel free to use it. I quite like how it acted in that.
Yeah. I mean,
Have you seen emojis used in Julia for in the language? So here, look, Julia for biologists. GitHub.
we can't see. Yeah, we can't see.
Oh, how come? Oh, I've stopped the share. Okay. I'll resume share. Maybe I am recording. No, not Bio Julia. So this is common. A reaction network, etc. People have used it with predator prey, right? Like rabbits and foxes and
Did you hear that image processing thing? They did it for a baking thing. And it was like image processing to make sure the results came out right, but they used to like signals underneath the media.
yeah. And yeah. Yeah, I've never used emojis, but go ahead in project 3 if you want to kind of go wild. We've actually specified in project 3, it's a slightly different coding style. I mean, you can do what you want, but when you're scripting and doing machine learning stuff and data analysis stuff, it's not like you're developing a program that's going to be reused again and again. Your code will be reused, but you can be a bit dirtier. So if we've tried to specify that in the project, right? So, if you find yourself copy pasting many chunks of code and they're repeated, do put them in a function. But in contrast to the polynomial project and the simulation project, this is more of a data analysis and machine learning experimentation project. So, in production code that you're going to use, you wouldn't want to have like numbers inside the code typically. You'd want to have them as parameters or right, things like that. But you can be a bit dirtier in that sense in project 3. There's a question. Let's see, am I just recording? Because now I thought I stopped the recording, but I didn't. Let's see. I'm just going to make sure. Yeah, this is recording. Okay. So back to this. All right. So the question, oh, no, the question disappeared. So the question was, want to make sure I understand the confusion matrix correctly. Does the 1107 next to 0 in the second row mean that what zeros were? Yes, that's what it means. So in this confusion matrix, but it's not 0. So the second row is associated with 1, right? So this means that 1107 ones were correctly identified as ones. The MNIST data set is a balanced data set, roughly, not exactly. There are 10,000 observations, so there are about 1,000 one digits. Clearly more than 1,000, because we had here at least, the sum of this row is going to be the number of the one digits, right? Maybe about 1,200.
So it's like when I equals J, basically, it's correctly identified.
Say again?
So like when I equals J.
Yeah.
It's correctly identified or something like that.
Yeah, that's what it is. So that's how we did it. So it's just this is a bitwise and or an element-wise and between the predictions is I and the test labels is J. That's how we create the confusion matrix. Other thoughts, comments? Okay. Now, I just in the interest of time, I won't. Well, let me actually just run this very quickly, just so you actually see that all this runs quickly. So, train labels, etc. I'll go down. I've done this before. So, oh, I didn't define A. So let's define A. So the computation of the pseudo-inverse, it's now computing the pseudo-inverse of this A, and that's it, it's done. Okay, this was like the learning process. Okay, but this learning process used kind of the beauty of linear algebra and state-of-the-art algorithms for computing the pseudo-inverse. Okay, you cannot always do this. And then here we are doing the classifier, and that's it. We're doing 10,000 predictions as this is running, and that's it. So the time it, of course, this was loaded before. There's always a bit of pre-compilation time, etc. But this kind of goes to show two things. One, well, Julia is fast, but frankly, with NumPy and Python, it would be almost just as fast in this case because pseudo-inverse will also be a closed routine. The second thing it shows, which is more important, is that machine learning is not so hard in a sense. Well, we can get 86% accuracy with just a linear predictor. Okay, but let's now just take it just a step more and move on to some gradient-based learning. So we could have done, and you're actually required, you're asked to do this in the project, what we just did, you're asked to do this on the project with gradient-based learning. Okay, so the idea of the gradient-based learning, gradient descent is in a sense well, I wouldn't say the dumbest, but the simplest learning algorithm. It's really not the simplest because the simplest is to try different points. So you've got in optimization, not learning. So when we speak about optimization, you're optimizing a function from Rn to R, okay? N here was, I should call it maybe RP or something like that, 785 dimensional. Zeroth order methods, they don't use gradients at all. There's something called Nelder-Mead, and there's other things. They can try different points, do triangulars in between, right? You can just try random points and see what's best. There's all kinds of things. But when you're looking over huge spaces, you just can't try things like that. You get to first order methods. First order methods use gradient information. So the general idea is you're standing on Mount Kuta, assume that Mount Kuta burned down. Let's hope it never does. Okay, so there are no trees, nothing. So you can walk, okay, you're not gonna hit a tree, and your eyes are closed, and you just find, like, kind of using feeling, you're seeing the direction of the gradient, and with lowest, well, the negative gradient, okay, the gradient points up, you go in the steepest direction, you take 3 steps, and you start this process again. Okay, so you get to the kind of the bottom of the mountain. I guess you'll get to the river, well, or to the gap, I don't know. Depends where you start on Mount Kuta. Okay, so that's gradient-based minimization. Maximization opposite. Machine learning, we typically minimize. You have second order methods that actually use Hessian information, curvature information, so second derivative matrices. Okay, they are not so common in machine learning just yet. When you saw in the prac last week, logistic regression, GLM actually used second order information, but on very big problems, it's still not as common. However, people are working on that and trying to use second order information in machine learning. So gradient descent is in a sense the method used. However, often your data is so big that it's hard to compute the gradient. So keep in mind, the data is fixed here. Look at if you're looking at this gradient, for example, here. The matrix A, and the matrix A is just above, the matrix A had data in it. And okay, we had here 60,000 observations with 784 features, no big deal. But if we had 1 million observations on images that are 300 by 300 RGB, so that's 1 million times 300 times 300 times 3 RGB, the data would be kind of too big. So actually computing this gradient just like that or storing it in memory is not doable. Okay. So while we would like the gradient, what we can do is we take a slightly different approach. So we can either do something called stochastic gradient descent, and that's often the thing that's kind of taught theoretically and analyzed in certain ways, or we can do something called mini batch gradient descent or use mini batches. So let me describe this now, and this is also a new project. So the general idea is that if this is like the matrix you would use, then with stochastic gradient descent, every time with pure stochastic gradient descent, instead of using the whole matrix, you're going to use just one observation. So this pink line, which I chose, is just going to be like randomly selected. And you'll assume that's the one observation I have. Okay. And with each iteration, you'll do that. Your optimization then won't take you directly in the true gradient, because it's only going to use a very small subset of the data, but it's going to put you in the general right direction. And actually what people found in the last couple of years, that noise is actually good, especially if the problems are non-convex and you have many local minima. That it's kind of like it's a bug that has become a feature, right? You're actually moving not in the right direction, but it's sometimes useful not to move in the right direction. But there's still a lot of research and debate around that. But anyway, that's stochastic gradient descent. The other approach would be to slide this thing, not necessarily work on one observation, but work on some subsets. So let's say on 1,000 observations each time. So let's say that this box is now of length 1,000 observations. So you move on 1,000 observations and you call that a mini batch. It's just a batch. Mini, I don't know why, because machine learners like all these terms. It's a mini batch, all right? And then you move to the next mini batch and the next mini batch and the next mini batch. So with our data set, if we use mini batches of size 1,000, how many mini batches are we going to have? So just to see we're speaking about the right thing. Again, mini batches of size 1,000. No interaction. Now, we have 60,000 observations, right? Mini batches of size 1,000. So we'll do this like 60 times. After 60 iterations like that, and each time we'll do a gradient step. We'll move over the data. These 60 times, another bit of lingo in the machine learning world, specifically in the deep learning world, that's going to be called an epoch. An epoch is one pass of the data through all the mini batches. Okay, so let me now show you this. All right, and you need to do a bit of this in your project as well. You can use some of this code here, and then some other bits you need to obviously fill in, kind of similar to the gist of previous project. So this is not useful for the project. This is just demonstration code, but let me just explain this. So what we're doing in this example, actually go first to the plot. The next bit of code is kind of a bit closer to parts of the project. So here, this is kind of this is not the digits data set. This is a much more reduced example where X, there's only a single feature, and Y is the label. This is a regression problem, simple linear regression, okay? I mean, we've created this kind of synthetically from these observations, but that's not so important. So there's some beta 0 and beta 1, which are the two parameters, the slope and the intercept. The intercept and the slope. Okay, and these are the data points. And what we're doing now is we're doing a loop similar to this one that I alluded to here with gradient descent. This was a gradient descent loop. Okay, this is like a complete gradient descent loop in unit 3. But now we're doing, every time we're choosing a random index from the data points, right? A random index. And we're only computing, this is like it's still an explicit gradient computation, but we're only computing it for that point. So if you look at the trajectory, and we're recording the trajectory too, just so it creates these nice plots. If you look at the trajectory kind of in parameter space, you've got beta 0 and beta 1. And the actual point we'd like to get to is this red one. A lot of people have been researching this in all kinds of different ways, etc. There's some stochastic processes involved. There's other things. Some of the nice properties of stochastic gradient descent is that when you're far away, you actually move almost like you're in gradient descent. And you know, there are ways to argue that theoretically. And then what you actually enter this valley where you're actually moving quite slow, and a lot of iterations are going here, and you're never going to stop at the actual real point. However, machine learning is not mathematical optimization for the sake of optimization. It's learning. And often you don't have to find the exact minimum, certainly not the global minimum, of the loss function which you engineered yourself. You just want to be in the right vicinity. And when you do this, then you get the blue line, which is, you know, it's not exactly the red line, which is a ground truth, but that's good enough. So that's like stochastic gradient descent. But this is not a practical example. This is just simple linear regression. When you get to bigger problems, stochastic gradient descent is going to be, mini batch gradient descent or stochastic gradient descent is going to be used. And this example, which I want to speak of now, uses mini batches. But for this, first I need to introduce the one model up, okay? Now, in your practicals this week and practical I, the last practical, you'll see the logistic regression model, okay? The logistic regression, I mean, who's heard of logistic regression? You've used it before. Somebody, stat 1301, you know, they show a line, they say you can't pass a line through probabilities and lines go from negative infinity to infinity, so you get this kind of sigmoid curve. Logistic regressions are great for probabilities of events happening. Okay, for predicting proportions, for predicting probabilities, for binary classification. Here, to make this lecture short, I'm going directly to like multi-option logistic regression. So some people call that multinomial regression, or we called it here logistic and softmax regression, Okay, multinomial logistic regression, there are many words for it. So let me just explain the model. Okay, this is a machine learning model. So this one here is logistic regression, okay? And this one here is logistic softmax regression. Let's start just with logistic regression. So a logistic regression model is just like a linear model, just like we had in linear regression, just like a linear model, only you pass it through something nonlinear at the end. This is the sigmoid function, okay? The sigmoid function, it's a function that looks, I should of course plotted it, but I'll just draw it. It looks like if this is 0, the sigmoid function just looks like this. It's actually a distribution function. Like this is 0, height 0, and this is height 1. Okay, and it passes through the point half. So a lot of early machine learning has used a sigmoid function, logistic regression uses a sigmoid function, etc. And what we're doing is we're taking our 784 dimensions or whatever you want, your feature vector X. We're doing an inner product of that with the weight vector. We're adding the intercept, but then we're passing this scalar value, which we labeled Z here. We're passing it through the sigmoid function. So y hat is going to be a value between 0 and 1. Okay, that's how logistic regression, well, that is the model, right? If you're a statistician looking at logistic regression, or also when you were in the practical last week and there was just a bit of logistic regression with GLM, then there are also statistical assumptions under logistic regression. It's the most highly used model in biomedicine, by the way, right? Doctors know all about logistic regression, they use it a whole lot. You're a machine learner using logistic regression. Well, what you're saying is, okay, that's going to be my model, y hat. If I want to make a classification problem from it, I'm going to put a threshold. And maybe if I don't know anything better, I'll just put the threshold at 1/2. And if I get to be over 1/2, then I'll say it's a positive sample. Otherwise, it's going to be a negative sample. That's with a binary classification problem. That's how you'll use logistic regression. And when you train the logistic regression model, under the hood, you also have a loss function, which is called the binary cross entropy loss function. Who's heard of cross entropy in some other context? No, they're at home. Okay, cross entropy is a measure that takes two probability distributions and gives you a number. And it's like the distance between the probability distributions, but it's not a proper metric in the mathematical sense that it's a metric. It's not symmetric, for example. But it's used in many places in statistics, and you might see it in other courses as well. And we don't need to deal with these details per se. All I want to say is with logistic regression, you have a loss function, which is not this loss function that you've been probably conditioned to know and love in other courses, which is a square loss. If you do logistic regression with square loss, the optimization problem is highly non-convex and it's difficult. That's just the property of it. Whereas if you look at it with this other loss function called cross entropy, which we don't need to get through with the details, then the problem is actually convex. Many machine learning optimization problems are not convex, but still using cross entropy works. Okay. So that's maybe a lot of buzzwords, but that's logistic regression. We'll see the example in a second. And on the more general, softmax logistic regression. So this expression should be familiar. Who remembers it from someplace? Yes? Big homework. Good memories? Varied. Oh, yeah. Okay. Depends who you ask. Okay. Fair enough. Okay, so in big homework, we just gave you this for the fun. I don't know who's fun, but somebody's fun. Okay, and that was to take the Jacobian of this, right? Why Jacobian? I mean, this is a function that takes a vector in Rk and gives you a vector in Rk. It's actually very simple. All it does is it just exponents each of the coordinates to give you something non-negative and normalizes that by the sum of the exponents. So softmax can get like the numbers 2, 7, and 9, and give you a probability distribution associated with 2, 7, and 9. 9 would be most probable, 7 less, and 2 less. Okay, and these are going to be the sum of these probabilities are going to be 1. So we like it in machine learning, okay? And the reason we like it is when you're now going to stick this X here is going to be, again, your image, 784 dimensions. Let's multiply X now by a matrix W, okay? That matrix is going to be 10 by 784. So it's going to give us something that's 10 dimensional, okay? And then let's add the vector B, which is also going to be 10 dimensional. So now we got this thing. Some people actually call this Z a logit. That's like slang in the ML world. And this thing is going to be a number. Well, it's going to be a vector with 10 numbers, maybe positive, maybe negative, that just pass through this kind of affine, this linear component. Then we'll apply softmax to all of this, and we'll get a probability distribution. And that probability distribution is going to say, well, if that probability distribution is going to be concentrated, say, on the third entry, then we'll say that it's most likely that it's a digit 2, because 2 is a third entry, 0, 1, 2. Okay. So the logistic softmax regression model is simply this thing. By the way, to use it, once you know what B and W are, when somebody is trained what B and W are, is not hard, right? All you need to do is you need to multiply the matrix W by your image X, your vectorized image X, add the bias, stick it in this guy, and then, well, if you have a probability vector, how are you going to decide which are the right digits? So you've got different probabilities, you'll find the one that's most probable. Okay, so that's a softmax regression model. Now, to tell you the truth, this, welcome, you've now seen a neural network. Okay, I mean, a linear model is also a neural network, but this is really maybe kind of an archetypical neural network. Neural networks involve affine transformations, like this thing, which I'll highlight now in orange, this affine transformation, followed by nonlinear transformations. Deep neural networks, you've heard about deep learning, deep neural networks, simply apply this thing again and again and again and again and again and again and again, like maybe about 6, 7 times, like cascading times. And they actually have great performance, but they're also hard to train, and they can have a hell of a lot of parameters. Okay, but this model is, you know, it's already kind of a non-degenerate neural network, but it's a shallow neural network. And that's as far as we'll get with neural networks in this course, but you know, you'll see that further in your career for sure, in one way or another. So let's spend a bit of time on this code. And this code kind of does a training loop, learning the softmax model. Let me actually put it in Jupyter here. Let's hope it works. Let's see if I run this. So I'm going to do something. And we'll spend some time speaking about what's happening here. Yeah. Okay. What was an epoch? Remember what the epoch was? What's an epoch? Yeah. 1 mini batch or all of them? Oh, no, one, there's no name for that. One, you just call it like a mini batch of rain, but when all of them. Just vocabulary tests, but this is like the lingo. And by the way, you guys are mathematicians. A whole bunch of people are doing this without really understanding the math. So, you know, going to this and having that edge of just understanding the math gives you a whole lot. But there's, you know, people speak about epochs, mini batches, dropout, normalization, batch normalization. There's just a few terms in this kind of deep learning world, which is people can use without going too much into the details. And epoch is one such terms. Yeah, and great question from the chat. Will the Jupyter notebook be left someplace? Yes, so there is in the course, this is the course GitHub. So we've got the folder console scraps. I've changed the name to, it's not console scraps anymore. It's lectures and console scraps. So this will be in the GitHub lectures and console scraps. But this is simply taken from the lecture notes and I pasted it in Jupyter and made it run. And it's running now as we speak. So what's it doing? And then we'll look at the code and probably spend the rest of well, maybe 20 minutes and then 10 minutes for something else just a bit later on what it's doing. So first of all, we're running for several epochs. My computer, you guys are far, and at home you're very far. At YouTube, you're extremely far, but the computer is going. I don't have a GPU also. I have GPUs, but they're Mac GPUs. So Julia is not making use of the GPUs. And this is not like there's a new M1 Mac GPUs. I don't have those either. So anyway, the CPU is crunching away. I think it decided to finish. And no, it's still running. We still have a star there. Oh, I could have seen this on the top right too. And this is called a training loop. The life of a deep learning engineer is looking at this thing. Okay. and often making a heaps load of money. I'm not sure why, because they're just looking at this thing. They're not looking just at this thing. They're also looking at TensorBoard, plots, etc. But adjusting parameters, this area still has a lot of alchemy. This is a simple model, but what you're seeing here is a training loop, which is kind of like a deep learning training loop, only miniaturized. So as we're doing this per epoch, we're seeing the loss. And this loss, again, I said some word, cross entropy. It's actually for multi-class, it's categorical cross entropy, but these values are decreasing. Great, so we're optimizing. Good, we're optimizing. Okay. Often on more general models, these things won't just always be decreasing because we're using mini batch gradient descent, and we can actually have increases too. So when you plot loss, it'll be decreasing with some increases, decreasing, increasing, etc. So we want to plot the loss. What am I doing every 5 epochs? I'm actually taking the test set, which I decided to call here the validation set, because in the world of machine learning, really test, you want to only test once in the end. Where validation, I've now changed the hat of test set to validation set. You can use it during training. And I'm actually seeing how the model that I'm training works on the 10,000 samples of the validation set. So when we just started, we started with a weight matrix that's a rand-n, that's a random normal. We could have used a distributions package random as well, but this is like a built-in rand-n, random normal. So just standard normal 10 by 784 matrix. That's a W matrix. Okay, we initialized this W, oh, sorry, it's here. We initialized the W matrix just to be garbage. And then we initialized the bias vector just also to be just 10 random numbers. So of course, if I would at that point compute the validation accuracy, and when you're doing your project, you can experiment with these things to see, what would be the validation accuracy if I just start with random things? What if I just start with random W and random B? What's going to be the validation accuracy? Number, yeah? Go for it. A ninth, a tenth, 10 digits, yeah, 0 to 9, 10%, right? So often you might have a bug, for example, when you're doing this and you forgot to subtract 1 from the digits, for example, shift by 1, and you go, oh, 10% accuracy, this thing's not moving, right? Because everything that was a 6 were a 7 or something like that. But of course, when you started, yeah, it's junk. But that junk is getting good quick, because after 1 epoch, and we're using here mini batch sizes of 1,000, okay, so the epoch had 60 iterations of gradient steps, and the gradients weren't exact gradients for the whole data. They were only gradients for 1/60th of the data, okay? Then after 1 epoch, we already got a classifier that got us at 70% accuracy. So why am I not printing the validation accuracy every epoch? Just speed. I just don't want to waste. I want to train. So, you know, I did the training loop that it will print it on the first epoch and then every 5 epochs. Yeah.
I assume that the accuracy down with this.
Yeah. So there often people speak about what's called human level accuracy, right? So we cannot do better than the annotators. Right. So some people would then look at the digit and wait, was that a 1 or was that a 7? Right. And right, there's a bit of human error in there. So when in this type of machine learning, when we're trying to mimic human performance, we're always trying to get to what's called human level accuracy. Right. But that's kind of not a mathematical thing. It's just kind of what we can get to. Now, if you're doing machine learning on something like the Melbourne housing data, which you won't do in this project. For this project, the first part, you look at the Melbourne housing data and you'll just do statistical kind of data frame mishmashing and stuff like that, which is very important. You know, but if you were going to, let's say, predict house prices, of course, you're not going to get human level accuracy because humans are not statistical machines, right? Then you're using it as a statistical model and your accuracies, you know, can be much lower, right? But these types of data sets are really, this is the AI that's trying to replicate human level tasks. Yeah, if you look later on Wikipedia MNIST, you'll see state of the art on MNIST 99% or 98% with convolutional neural networks. We got here on my laptop with just a bit of code to 92%. So we did better than the linear model. It seems that the difference between 86% and 92% is not much, but 86% can be unusable and 92% can be something that we could work into an application already, right? So those last couple of percents are always, of course, very, very hard. So there's a whole industry of people that are working on state-of-the-art ML for kind of on benchmark problems to improve the accuracy, mostly on ImageNet. MNIST is more of a toy for these days. Okay. An epoch takes after a bit of warm-up, took about just under 5 seconds. And that's it. Any questions about the output so far? All right, so let's look a bit at the code and just understand a bit what's happening. Now, this code is almost, I know some of you said that you didn't like in project 2 that we gave code and you actually reused the code, but there's also something to learn there. And a developer often goes to other people's code and adapts code. That's like what you do, right? So you can spend 5 hours of developing, of which a whole hour net was going to Stack Overflow all the time. And that's valid. That's a good thing to do. So this code is actually going to be somewhat similar to the type of code that we recommend you use for some of the tasks in ML in the project. Okay, but there need to be some changes, and you'll understand them when you look at the project. We'll speak more about the project tomorrow. So let's just go line by line and speak about a few things. So first of all, we're using the package Flux, and like any deep learning framework, Flux can have like almost one-line commands that would train things. Here we're using it not in kind of the same. We're kind of going under the hood a bit, okay? And what you need to do with the project is even use it a bit less. And all these other packages, not a big deal. And these are some functions coming from Flux. I'll explain them as we get to them. We're setting the seed, so this example is reproducible. I must say that machine learning training, deep learning training in general, is very hard to reproduce, even if you set seeds in industry, because often you're running on GPUs and there's concurrency. So it's like not a reproducible process in many ways. Okay, so it's unlike, say, your simulation in project 2, set the seed, let this thing run all night and it's reproducible. It's beautiful, right? There's not going to be some little cosmic dust that will flip a transistor in the computer and something will happen. I mean, unless you really run it a whole lot, but machine learning is hard to reproduce. But in this case, it's running on my CPU, etc. It should be reproducible. This is just a test set. The reason we have the test set here, this is like the X for test set, is just so we plot, do the validation accuracy every few units. Okay, so here are 2 one-line functions. So this first one gets an image, gets an X, and multiplies it, applies a matrix W to it, and applies the vector B. We didn't need to have this dot here. That's not critical. If B is a scalar, it's important, but otherwise it's not needed, right? So we're adding the vector B to this thing, and that's exactly this, B plus WX. Okay, and an image is already assumed to be a vector, and it applies the softmax to it. So this is what prediction is like. Okay, this is still not going to give us which digit it is. It's going to give us a probability distribution over the digits, which is also, by the way, important. Sometimes you don't just want to know what digit it is. You want to know it's likely that it's the digit 9, maybe with 80%, but there's like 10% that it's the digit 4, right? And, you know, you could still use both numbers, like the second most likely. This, what does line A do? Line 8 uses that prediction, okay, and actually sticks it in argmax. And I've already said why to subtract 1, just because indexing in argmax of a vector, right? So argmax of a vector, argmax of the vector 2, 4, 8, -3 is going to be 3, because the third entry is a maximal, but you know, indexing would go 1 to 10, but we want digits to be 0 to 9. So these are like the 2 functions of the classification. So these functions, just putting things in context in this kind of whole sphere of supervised learning, they're the functions that you would use here in this ellipse, right? That's like the model getting a digit from the world with W encoded in there. W is like the parameters. By the way, a whole lot of effort of a machine learning engineer is actually getting those W's when your W's are like 80 megabytes or a gigabyte, getting those W's into the code and managing them, right? You don't want those W's in GitHub because you don't want binary stuff in GitHub and stuff like that. That's like a whole other kind of practical thing. But W, the code, the computer code, when people speak about like an AI model, it's those numbers. It's that W in the B. It's the weights and biases. All right. So now we're looking at the train. This is a training loop. All right. So that's like this guy. Okay, we do some initialization. Sometimes you can do it in a different way. Then this optimizer ADAM, that's not so important, but the ADAM stands for adaptive stochastic. There's no S there, I don't know why. Adaptive stochastic gradient descent, or maybe this stands for something else, but that's adaptive stochastic gradient descent. That's kind of the most common slight variant of gradient descent algorithm. But don't worry about it too much. It's like gradient descent plus a bit of momentum plus a bit of correction for other things, but it's really gradient descent. You do not have to use this in your project because you're going to use a gradient explicitly. Now, this is a loss function. The loss function takes an observation or a collection of observations batched together and the labels. And what it does, in this case, it uses cross entropy came from the flux package. I didn't actually show you the formula for cross entropy, but you could use that almost as a black box here. It came from the flux package. It gets the prediction. And it gets, so this is going to be like a probability distribution over of length 10, a probability vector of length 10. These things I've highlighted, right? Logistic softmax predict. And it gets a one-hot batch vector because you're going to compare the vector of like 10 probabilities with a vector 0, 0, 0, 0, 0, 0, 0, 1 of someplace, 0, 0, 0, 0, like a degenerate probability distribution, which is like the right one. So this is a loss function. Now, this I've seen people do in the project a lot, define functions within functions. You can do it when you need, because like the scope of this loss function is really within this training loop, but don't do it overly, right? You only need to do it, like if you need loss outside of the training loop, then define it outside. It's not so common to have a function defined inside a function. So we start with some loss value, which is garbage really, and we just do a counter for the epochs. And then this whole thing is called the training loop. So often a machine learning professional would still code their own training loop. People don't know this. People that are kind of outside of the field, they don't think that machine learning engineers code, but no, you code training loops all the time and you kind of adjust this kind of scripting code all the time. Now this loop is running forever. Well, is it? Where does it stop? On which line does the loop stop potentially? Where do we stop? Just to get you to look at the code. Yeah, the break in line 47, right? So often when you see a while true, you can either say, okay, this dude wants to go to just heaven and continue to run forever, or no, there's going to be a break someplace. So this is actually not the common way. Often people just run for like a set number of epochs because there's like a computation budget, you run for a set number of epochs. Okay, but here what we're doing is we're stopping, and our stopping, just, interpret this. This is one stopping criteria. The difference between the loss is already insignificant. This is a bit of a primitive stopping criteria, right? So if this happens, then break. You might ask, why am I taking absolute value? I mean, isn't loss always going to decrease? No, on more general problems due to noise or non-convexity or stuff like that, the loss function can actually go up. So even, because it'll have some fluctuations. But this is like one stopping criteria. You can just put a for loop here and run for, after you have done this, we will see, this thing trained in about 45 epochs. This is when, right, the difference between these two was not too big, and then it decided to stop, right? And you could instead put a for loop for this. And this is just a recording of what the previous loss is for the loss. Okay. Now we get to the meat. I'm vegetarian, but, so we get to the tofu. Okay, so let's loop over mini batches in the epoch. All right, so these lines 27 and 35 are just my primitive way of kind of recording time. You've seen this also in unit 2, right? So this is not timing like benchmark tools. You actually, when you're a machine learning engineer, you look at stuff, you actually want to train, you have budget, right? You want to go and want to put this overnight. You want to come the next day. You want to understand how long an epoch takes. So having this information is not just for the classroom. This is like operational, right? So the thing is, machine learning engineering is kind of like lab work where you put stuff overnight or for a day or two and you change things, you come back the next day, et cetera. So you actually want to know how long, this thing is going to ferment, right? So that's what you do with this timing, start time and end time, time in nanoseconds. Okay, now what are we looping over here? We're looping over this phrase we learned, mini batches, okay? Julia actually comes, an iterators package is a built-in package, just like random and just like statistics and just like dates, okay, and just like linear algebra. Iterators is a built-in package. The partition function from the iterators package can take this range 1 to 60,000 and just create like ranges of size mini batch. It's kind of cool. Okay, so then you can kind of iterate over the ranges, right? So we just want to, each time when you do this here, this batch, when I get to line 30, batch is already a range that can be like index 1001 to 2000 or 30,001 to 31,000, right? This is what the iterators does. And I think even if mini batch size wouldn't divide and train, it should probably be okay. Often you see that the last mini batch is a bit smaller, right? Because it kind of doesn't fit exactly. By the way, in practice, a lot of times you choose a mini batch size based on what can fit in GPU memory. So we're not running in GPU, but when you do this on much more complicated models, this thing is going to run on a GPU or multiple GPUs. And you want things to be in GPU memory because then all these computations like the matrix multiplications and the gradient computations are parallelized and they're fast. So you just experiment, you see, well, can I do a mini batch of 30 or 40 of 60, mini batch of 1,000 is much, but our data samples are small. All right. Now we come to the real technology, line 30. So in unit 3, Paul Bellet has shown you guys very briefly automatic differentiation. Automatic differentiation is not symbolic differentiation like Paul Verbig's stuff, Maple, Mathematica, etc. And it's not numerical differentiation like you did in that problem 14 or something in big homework. It's actually a different form of differentiation where the chain rule is used recursively, and what we get is a numerical expression based on its subcomponents. So this gradient function, this is like the real power horse that we're using from Flux, and Flux uses a package under the hood called Zygote. And it's computing the gradient of this loss function with respect to the parameters W and B. Okay, this is like the magic here, really. Actually, in the project, you're asked to, because logistic regression and softmax logistic regression and linear regression have explicit terms for the gradient, so the project refers you to those explicit expressions, you're asked to replace this line 30 or context of this line with like a symbolic expression. Often we don't have symbolic expressions when we do this gradient-based learning, but for these models we do. But here I was lazy, so I just used automatic differentiation. Okay, but I don't want to say this is like the actual gradient computation. In deep neural networks, which again we're not covering, but you get a bit of a prelude for this. Has anybody heard the phrase the back propagation algorithm? Just kind of listening to stuff. This would be the back propagation algorithm because it would actually do like run through all the network, fill forward, and then go backwards, do backward mode automatic differentiation. This is where the compute happens. That's what taking most of the time. This line 30. Okay, so that's a derivative. And then what we're doing here, this is something that's kind of not so common, but you can do it. You can iterate over the elements in a tuple. I mean, you can. I mean, typically you do it over arrays, but why not in tuple? Update exclamation mark. You already know what exclamation mark in Julia is, right? It's not a reserved symbol. It's just notation. This is going to update both the optimizer. So the optimizer has some state and the parameters based on the gradient evaluation of those parameters. So lines 30 and 32 are like the gift we got here from the deep learning framework. You can do without those lines by just doing it manually. So the practical is going to show you this manually for logistic regression. Okay, and you can do it, replace these and fiddle, and of course things will break a bit, etc. But then you'll get it to work for softmax logistic regression, right? So it's kind of remove the high tech from here in a sense. It's still going to be high tech. I mean, it's computer after all. But that's it. So what you're doing here is you're computing a gradient and you're moving in the direction of the gradient. And you're not moving exactly in the direction of a gradient. You're using the optimizer, but in the practical, you'll see this where you're actually moving in the direction of the gradient, just like this. Value equals value minus some constant, which is called the learning rate, times the direction of the gradient. I've spoken this whole lecture, I still haven't said the word learning rate. So this 0.01, that's the learning rate. It's like I'm in Mount Kuta and I'm going down. Well, I found the negative gradient. When I said before moving direction of gradient, I meant moving in the direction of the negative gradient. We're minimizing. Gradient points up. Okay, so learning rate is that gradient, how big of a step I'm going to do. Okay, great. This is really it. This other bit is just the fluff. So we're increasing the epoch. We're computing the loss. Loss can be computed matrix-wise over the whole matrix X. We're printing, here's the epoch, and here's how much time it took, and here's the loss. That's exactly this printed line. And then this happens every 5 epochs or at the first epoch. We're computing the accuracy on the validation set and printing this accuracy. And we decide to stop only every 5 epochs. Okay, we don't stop every epoch, simply because this way it prints the accuracy. So this is like a simple training loop. But often you find yourself looking at these training loops, right? It's not a complicated algorithm. It's just doing stuff that, again, the technology is here. So any questions about this one? Sorry, I'll pull through till 7. Okay, we always in this class, we cheat the system. We teach till 7, right? That was like, except once or twice, we didn't cheat the system. Any questions at home? No. Okay. So where do we go from here? So after we've seen this, and you see that you actually get a model that gets 92% accuracy, let's just speak just about a few more things. So one might be inclined to pool and get the best loss and get the best fit of the training data, right? But this example, this is a very simple example that shows you that can be a bad thing. We're now moving from digits to a much simpler domain. Again, we just have X and Y. Ignore the blue line, ignore the red line for a second, okay? If you were to just look at those data points, those triangle, those diamonds and the circles, you might think they're coming from a similar process, right? They're just samples. Now, imagine that we only sample the scene data points, these triangles. Okay, then we go, I have a supermodel. I'm going to pass through all the data points. Okay, so what I'm doing here, or what we're doing here, is actually, that's the code that does it, is polynomial interpolation. This is called the Vandermonde matrix. It's kind of cool that you can pass a polynomial through these data points, and the order of the polynomial is like the order of the data points. But of course, this is overfitting, right? I mean, because, you know, it was a matter of luck that we sampled those diamonds and not those points. I mean, a much nicer model for this case would have been just a linear model. a line passing through the points. Okay, so they were completely off. So by analogy, and you got the code that does this above, but it's not of any use for you at the moment. Okay, by analogy, with machine learning, you can also do the same. You can take training data, you could feel very good and you're getting great performance on the training data, but actually on this thing on the side, on the validation data, things are becoming bad. Okay, so that's in general called overfitting. A lot of if you do a full course on machine learning, there'll be a lot of discussion of overfitting. There's something called the bias variance trade-off, and this is not bias like we said before the intercept. Here, bias means that you're actually getting the wrong thing, and variance means that you're doing overfitting. So all I want to say is this is like a lot of machine learning deals with that. So because of that, there's kind of this general paradigm of dealing with data, and people use different terms, but this is the terms I chose for here. So you can treat your data in general, okay? Anything that's training is like this thing we just ran before, or the thing that the machine learning engineer does when they adapt the model. Production, well, when we started the class and I wanted to show you this example of this actual ML thing that works, or if I'll speak to my Siri now, that's production, okay? So production data is unseen. The machine learning engineer never sees it. Other training data is seen, it's collected. Before we said we split the training data into a training set or train set into a test set. But really what you can do is you can take the scene data and do a training set and a development set, also known as a validation set, and you really keep the test set aside. You don't abuse the test set. You don't check the model over it and try a different model and try different variation, try something else. You really keep it on the side so you can report then to management or whatever, how good the test set was. Right? In practice, frankly, this is sometimes abused a bit, but you don't want to use a test set too much. And then there's also a method, maybe we'll say just a few words on it tomorrow, where you can, if you don't have, what I want to say here is that there's like a triple split, train, validation, test. Okay, but up to now in the lecture, we only had train and test. Okay, so you can do train, validation, test. And the validation would be like this thing. You see, I call this in the printout validation. While you're training, you're actually looking at the validation. People often call the validation the holdout set. So there's also a technique called K-fold cross validation, which does that. That's it. So what we're going to do tomorrow is spend, oh, sorry, I said K-fold cross validation. K-fold cross validation is a technique which, if you don't do this separation, then you actually can do, you can, I'll explain this tomorrow because we just need just a bit more time for that. It's a nice technique when you don't have a lot of data. So tomorrow we'll spend time on tree-based models, which are completely different in a sense than these gradient-based models. Here's an animation. Let's just put it on before tomorrow. But that's only a small part of your project deals with tree-based models, only the differentiator question really. Where's a tree-based model? Let's just put the animation for it. Yeah, okay, so here's a tree-based model. It's learning to classify. Okay, so we'll understand this tomorrow. So maybe we'll spend about half an hour on that, and we'll spend half an hour discussing the project, giving tips for the project in general. Okay, any questions? All right, thanks for the patience, your patience, and see you tomorrow. Bye.